All right, hey, I got another one. I don't know if this is number 4, number 5, but we're moving along here. So I got a question. It's 18. It's actually the hard part of 18, 18G, but might as well build up to it. So why don't I just start at the beginning and say, okay, let's look at number 18 from chapter 15. And so I'll begin here. It says a 2-kilogram object is attached to a spring and it is placed upon a horizontal surface. Okay, so maybe here is the object, here's the horizontal surface, here's the spring attached to a wall, something like that. And then it says a horizontal force of 20 newtons is required to hold the object at rest while it is pulled 0.2 meters from the equilibrium. All right, maybe I'll just draw another picture. I'll make a dotted line. That's where the object was, but now it was been pulled forward by 0.2 meters, so the spring is now stretched, and it's being held at equilibrium by a force of 20 newtons. And so the key is to realize then that the spring would be pulling back with 20 newtons, because we know the sum of all the forces equals ma, Newton's second law. And if it's going to hold it there, the acceleration is 0, so the net force needs to be 0. So that means the force pulling it there, the 20's got to equal to what's pulling it back, which is the spring. And so that gives us some helpful insight to know how much the spring is pulling based upon how much it is stretched, because that is really where the spring constant comes into play. And I think that's one of the questions along here. It says the object is now released from rest with an initial position of this 0.2, okay, and is subsequently undergoing simple harmonic motion. Find. And it says A, the force constant of the spring. Well, the force constant from a spring is this minus kx. So if we take the magnitude of the force and we divide it by how far we stretched it, we get the spring constant. And so that was my point here, that if I pull it with a force of 20 newtons for a distance of 0.2 meters, is that 100? Must be here. Move this to here, give it 0, 100 newtons per meter. So there would be the first part of this. What's the spring constant here? And so 100 newtons per meter. Going on to part B, the frequency of the oscillation. Now, maybe this is worth repeating kind of quickly here. But the sum of the forces equal ma. If we're talking about only a force horizontally from a spring, when we add all the forces, we just get minus kx. That equals to m. A is the second derivative of position. Move the m to the other side, and let me take a moment to say this again. Anytime you ever see an equation where the second derivative of something equals that same function with a negative and this stuff out in front, then this stuff out in front, which in this case is Km, is the angular frequency squared. And so to do all these problems in this chapter, that's what we do. We write out the forces or the torques, and we set it equal to Ma, or I alpha, if it's a rotational problem. And so in this case, it's horizontal, very simple, just one force. And we figure out what the omega is. So the omega would be the omega then would be the square root of K over M. And as we just said in part A, the K is 100 and the M was, let's go back, 2. And so this would be the square root of 50. Square root of 50 is 7.07. Now that's the angular frequency, and they ask for the frequency. So angular frequency is 2 pi times what we call the linear frequency. So linear frequency is more of the physical thing. It's, look, how many times does it go back and forth in a second? Let's say 3. Okay, so if you had something that was going around in a cycle 3 times, 1, 2, 3, And if we multiply by 2 pi, that's how many radians. That would be its angular frequency. How many radians did it do? Because it would be 3 times the 2 pi. So that's the mathematical connection between the angular frequency, which is probably more useful when we're doing mathematics, versus the normal frequency, or what often is called the linear frequency, because that's more physical. So physical, mathematics, we need them both. And this question, I believe, sometimes it's confusing, but it looks to me like it is really asking for the physical frequency, the linear frequency. So we need to divide this by 2 pi. So divide by 2, divide by pi, and we're looking at 1 and an eighth, 1.125. And so that's the, goes back and forth, 1 and an eighth in, 1 second. All right, well, let me move on to another page here. And let me put a little paper underneath it so it doesn't bleed through. Let's look at C. C says, I lost the page here. The maximum speed of the object. Well, without necessarily rederiving it, but it does come from the equation of the position. And of course, the position would be the amplitude times the, in this case, it started at its maximum and went back, so I'd call it a cosine, omega t, and there'd be no phase. And then, of course, if you took the derivative of that, you'd get velocity. That's why you would have the a derivative of a cosine is a negative sign. Let's see, sign. Yeah, negative sign, and the chain rule pulls out an omega. And so that thing out there is its maximum. And I said I wasn't going to derive it. I lied. Okay, but there is what we did in class and the textbook. This is the equation for the maximum. All right, so we said the omega a moment ago was the 707, and then the amplitude was given by, we pulled it and let it go, so that's the 0.2. And so grabbing our calculator, 7.07 times 0.2 is a maximum speed of 1.414 meters per second. And so there's our maximum speed. Oh, and actually there's more to this. Hang on here. It says find the, let's see, the maximum speed of the object and where does it occur. Well, I don't think we need to go back to the equation, although I guess, it'd be a little bit, maximum of a sine function is a little bit after you release it. A sine function looks like this and gets to its maximum, which is the quarter of a cycle as it goes back. So I guess I would say, it's back at equilibrium, or it's back at x equals to 0. So maybe I'll just put that at position x equals to 0 and call that good. Okay, then on to D, and again, I haven't really got to the main question. The main question was G, and rightfully so. I think G's the hardest one on here. But D says, find the maximum acceleration, and where does it occur? Well, again, the maximum acceleration occurred, or was equal to omega squared a. And again, this time I really won't do it, but take the derivative of that again, you're going to get another omega out here, and you're going to get an omega squared a. And so this would be that's the square root of 50. So when you square it, that would just be a 50 times a 0.2. So what 50 times 2 is 100, and 1 decimal place makes 10 meters per second. Or so, excuse me, was this centimeters or meters they pulled it? 0.2 meters. Okay, so that was meters per second, and that's meters per second squared. So we should get about a 10. And of course, the other part of this is, well, where does it occur? And let me see if they just ask for the maximum absolute value. Find the maximum acceleration of the object, and when does it occur? And where does it occur? Okay, so we start out with it over here at point 2. And that is the place where the spring is stretched the most, which means it has the most force, which also means it has the most acceleration. Now, it's in the negative direction. The pull is this way. So mathematically, you might want to call that the minimum. But in terms of absolute value, I would say that's one of the locations. And then when it moves back to the origin, x equals to 0, and then continues on until it gets to negative 0.2, again, that's the furthest stretching of the spring to the left. Then, or I guess compression of the spring, the way I've drawn it, so the furthest compressing of the spring to the left. And the force, of course, would be pushing it to the right. And so it would, the force would still be this, or magnitude of the force would be kx. So you would have the same amount of force whether we're at a plus 0.2 or at a minus 0.2. So that would be the greatest force and therefore also the greatest acceleration. So I guess the best answer is plus or minus 0.2 meters. Although, like I said, if you're thinking more along the lines of mathematics than physics, you might not be thinking about the magnitude of it. But I get the distinction that the author is talking about the magnitude of the acceleration. And so it's both of these are the correct answer. But truly, this one is the only one positive. That one's negative. So maybe I would say negative 0.2 meters. In fact, that gets me kind of curious. Let me flip over to the answer key. The answer key says what? So they say plus or minus, and then they write it plus or minus a. But I don't know why he doesn't put what a is. A is the 0.2 meters. But I like that they did the plus and minus, because I think we're talking about the magnitude of it, even though the author really didn't say that. But I think the author's thinking physics, not so much mathematics, and not calling this a minimum and then a maximum. It's the magnitude of it. But any of these and all of these would be perfect for a test and for an exam and to put on the solution, because it tells me you know what's going on. That's the big thing. All right, so on to E. E says, find the total energy of the oscillating system. The total energy. Now, let me maybe just draw this picture of it again. And so maybe here it is at equilibrium, and it comes over to here part way, and then eventually gets to its full maximum of 0.2. Then it comes back and gets the maximum the other direction at negative 0.2. But at some arbitrary location, how about this one? It has a little bit of potential energy from the spring and a little bit of kinetic energy. Now, at special locations, like it stretched all the way to here, it has no kinetic energy. It's all potential, and it's at its amplitude. And so because of conservation of energy, these two pieces, the potential and the kinetic, would add up to just what would be only potential at that point. Or, put another way, when it's here, it would only be kinetic energy and would have no potential energy. And so I'm going to put its maximum velocity there. And now that I write it out, if I know any of these three positions, an arbitrary position or full equilibrium or at its maximum, I can get it. In fact, I don't know which one would be better. I know these. So I'll just do this one. 1/2, the K we did way back in A, which was 100. And the amplitude is 0.2. And so grabbing my calculator, 1/2 times 100 times 0.2 squared is 2 joules of energy. And just out of curiosity, had I done this one, it would be 1/2. Its mass is 2, and its maximum velocity we did on part C here, 1.414, and square it. So those would cancel. Oh, yeah, and that's the square root of 2. So when I square it, I'm going to get a 2. So sure enough, the total energy is 2, whether you look at it in terms of all being kinetic or all being potential, or for that matter, somewhere in between. And I think that's how we want to look at maybe F here, because F is kind of an arbitrary point. Watch, right? This is because F says, find A, the speed, and G, the acceleration of the object when it is at a position of 1/3 of its maximum value. All right, well, I'll do F first. 1/3 of its maximum value. Now, maybe I'll come back to here, because using conservation of energy, I have 1/2 kx squared plus 1/2 mv squared at some arbitrary point. And so this arbitrary point is 1/3 of A. Has to equal to 2 joules. And I'm looking for velocity. Okay, so this would be 1/2. The K is 100. This would be 1/3 of A, and I'll square it. And then this would be 1/2 times its mass of 2 times its velocity squared, and that has to equal a 2. So maybe I'll work on this one first. This would be 0.2 divided by 3 to get the amplitude. I will square it. I will multiply that by 100 and multiply that by 1/2. So they're essentially telling me that the potential energy is 0.22. And of course, the total energy is 2, so the difference between those is the kinetic energy. So let me just go 2 minus that last answer, and that would be the kinetic energy. And since that cancels, that would also be the velocity squared. So let me take the square root of that. And so I get a velocity of 1.33 meters per second. But I think I said this on another video, and it's a little more advanced, so let me make sure you don't miss it. But, you know, when you ever get a question in mechanics that start asking you about speed and position, think energy. And that's what this is asking for the speed when it's 1/3 of the position, or 1/3 of the amplitude, which, you know, is a position statement. And so that's why knowing the total energy was really nice, because that plus that is the 2. And they gave us enough information to get that term, and we know that term, so we can then find what the speed has to be in order for it to make the total energy of 2. All right, so finally to the question that was really emailed to me, you know, what about G? How do I handle G, the acceleration? And there's a couple ways to do this, but I think the easiest one here is to remember that the acceleration is force divided by mass. Force is then kx, or at least the magnitude of it, and divide it by the m. And then we know these 3 things. We know the spring constant is 100. We know we have 1/3 of the amplitude is how far we pull it, and the mass is 2. So 0.2 divided by 3 is the x value. That's, I guess we did that one time before for the energy. Okay. And then so if I go times 100 and divide by 2, I get an acceleration of 3.33 meters per second squared. And so just kind of use the Newton's second law, force and acceleration. And so there you have it. Hopefully that helped.